All right, so you see this is due on February 8th. The first assignment will be the easiest of the three. So the basic things that will be in here is you're going to have a system. So every year I make up a new example. This one we're going to look at robotics. First year we did, what did we do? Electric cars. Second year we did levitating trains. This one's a robotics application. So this is a really typical industrial robot. This is kind of the robot that really made automation really happen in the world. The Puma 560. This is the first really commercial robot that really took over and was everywhere. And so this is a pretty old classic robot. I doubt you can buy this anymore, but it's a pretty good system to kind of analyze. And so we're going to look at how we can control the position of link 4, which is this one right here, this one hanging down, or this one right here. And this is rotating about what's called axis 3. So you don't have to get too concerned with all the different axes in the system. It has 6 degrees of freedom. It's quite complex. If you really want to know how the kinematics of the system works, you have to take graduate level robotics courses. But we're just going to focus on a single link or an axis of this robot, being this one right here. We're going to look at modeling of this, modeling DC motors or servo motors going to be attached to this, and how do we control the position of this single link of a robotic system. So you can go through and kind of read the problem statement. There's going to be some things that I think should be review from your dynamics class in terms of how do you describe the dynamics of just a single body, and then getting the equations of motion, linearization, and then also some simulation and simulating for the system. And then that'll be project part 1. Project part 2 is going to be a lot with more simulation. It's going to be actually integrating multiple systems together. So part 1 says nothing about the motor that's connected to this. We'll start to connect the motor in part 2, and then part 3 will design a feedback loop to control the position of this system. Okay, so that's kind of the outline of the project. Any questions about the logistics of how this project runs? Okay. One last thing I forgot to mention. So homework, or the project submission is online. It's due February 8th at 11:59 p.m. You only have to submit one copy. So either you or your partner submits. Don't both think you're submitting and no one submits. That's happened before too. So if you both submit, we're just going to grade one of them. If just one of you submits, we'll figure out who your partner is, and we'll give you a grade accordingly as well. Right, any questions about that? All right. Okay, so if we look back to what we talked about on Friday, we were just starting to get into this idea of how do we confine a magnetic flux. Okay, so we have a magnetic flux that we can get from putting a current through a coil or a conductor in a coil form, and so that creates a magnetic flux, and then we can confine this by using ferrous materials. So the ferrous material will basically allow us to direct where this magnetic flux goes, and with this we can actually direct it to where we want it to go. So we can have it drive a motor, or we can have it drive a solenoid, etc. So we're trying to understand now how we do this. And so the first thing to understand is that the reason why we use ferrous materials is because they have a relative permeability and permittivity that is about 1,000 to 4,000 times better than air. Okay, so that's a huge multiplier. And so permeability of air, not so great. Permeability of ferrous materials is very, very good. And so we can actually direct magnetic flux. And it's basically just by constructing this and controlling geometry, really determine where the magnetic flux goes in electric machines. Okay, so we're going to start to work with some really simple ferrous structures and try to understand the magnetic flux running through them. Okay, and so the simplest one we can really think of would be just a loop. Okay, so we know that there has to be a loop, just like, I'll go back a second. Okay, so just like this coil here, oops, didn't mean to draw. Okay, so just like this coil here, which we have a north side and a south side, the magnetic flux lines always go from north to south. Right? And so Same way here. Sorry, I drew this incorrect. Oh, that's right. Never mind. Okay, so we have magnetic flux lines, no, going from north to south, right? Okay, so magnetic flux lines going from north to south, and so this always makes a loop. Right, so all the structures we're looking at here are going to have loops within them. So let's take a look at a magnetic circuit, and we'll be using this term quite often in this class, magnetic circuit, which I think should imply that we have some sort of loop, just like we have electrical circuits. And so this one of the simplest magnetic circuits we can look at is a ferrous structure that makes a loop here. So if we have a ferrous structure, so I'll draw this in isometric form to make it a little bit more clear. So basically, you went to the machine shop, you had them take a block of, say, steel, and you milled a little pocket or hole in it, and now you have a ferrous structure. Right, so you have this block of steel. If we look at what the cross-section of this block of steel looks like, this would be what the cross-section is. And now if we want to turn this into something that has a magnetic flux going through it, we need to put a metal wire around it to create a coil and then put a current through this wire. So if we have a wire going around here, we can now send a current into this coil, and by putting a current in this coil, we're going to get a magnetic field. That magnetic field is going to go now around this ferrous structure. And just a reminder, from Friday we had some assumptions. One of the assumptions is that all the magnetic flux being created by this coil is being coupled into this ferrous structure. Right? None of it is going out to the air. Obviously that's not true, but we're going to assume that's the case for the sake of this class. Okay, so some terms here. So some terms we're going to use often in this class. One of them is going to be magnetomotive force. We'll denote this by script F. Okay, so this is what magnetomotive force in simple terms is what drives the magnetic flux in the circuit. We have flux that we've already described. Right, this is from lectures on Wednesday and Friday last week. So this is in units of Webers. And then we're going to have a term that's going to be called reluctance. So we're going to give this a script R. Okay, so reluctance. And so reluctance you can think of, and I'll try and make this come full circle in a second, as a resistance in a magnetic circuit. So just like we have resistors in electrical circuits, this is going to be a resistance in a magnetic circuit, if you want to make analogies here. All right, so each of these individual legs of this magnetic circuit are going to have its own associated reluctance too. And so we can start to describe this. We can say that we have reluctance R1 here. On this leg, this is from here to here. Going from here to here around the circuit, we have R2. Going from here to here, we have R3. And then completing this circuit, we have R4. So I'm giving these different names because these could all be different dimensions, and therefore they're going to have different reluctances. Any questions about that idea? There it is not. Yeah. So if we're going to make a coil, obviously it has to go through something, right? So you could have it around like a cylinder of some sort of ferrous material. But we could also, if you wanted to, you could have, like say this was just like a big rectangular block, you could wrap a coil around the rectangular block. Now, for the circuit to be closed, magnetic flux lines are going to have to go through the air, right? If you imagine that, like for instance, imagine I just got rid of all that, right? Like say big rectangular block, then the magnetic flux lines are going to have to go through the air to get back down to the north side of this electromagnet, right? So we'll see a lot of examples of electric machines, electromechanical machines. In general, I guess this is probably pretty true, is that they have some sort of ferrous structure that creates some sort of loop in it. It's very inefficient to direct magnetic flux through the air. And then I'll bring in some motors too, and you'll see that the gaps between basically these ferrous structures are quite small, in the order of a millimeter or two. Okay, because basically the reluctance of the air gap is really, really large, and that makes it less efficient. And you can't make it too small that they're hitting each other, right? Either because that would be mechanical inefficiency. Right? Okay, so I hope I kind of showed how this is a circuit. We're going to look at and come up with electrical circuit analogies, basically so you can use all the tools that you learn in electrical engineering classes to this domain. Right? So this is a lot of the things we learn are always tied to electrical systems because they're really simple visual ways to describe what's going on in some sort of system. So the analogies that we're going to make here is that the magnetomotive force is analogous in a magnetic circuit so this is magnetic, and this is on this side going to be electric. This is analogous to a voltage source in electric circuit. So V is in volts. Okay, so this element here, this coil, in the electrical circuit analogy, we are going to represent as a voltage source. And the voltage source potential here is going to be equivalent to that magnetomotive force. Okay, so anytime you see a coil, you should think of that as a voltage source. So I'm using the word voltage source for a really precise reason here. I think, in my opinion, some of the electrical courses here do a disservice by doing a lot of DC circuit analysis, and they oftentimes call voltage sources batteries. And so a battery, in general, is thought as something that has a constant voltage potential across it, right? So if you buy a 9-volt battery, nominally that voltage provides you 9 volts. In this class and a lot of other classes, we're looking at quite often variable voltage supplies. So the term battery doesn't really apply too well here. So I'm going to call it voltage source. So this could be AC, it could be DC. We're not going to specify. We're just going to talk about it in general, right? This is going to be a voltage support source to our system. Okay, so we have this voltage source given by script F. And then we're going to then fill out the rest of the circuit. We have a reluctance R1, which we're going to represent as a resistor element. So that's our standard symbol for a resistor. That's R1. The flux then flows around in this direction, goes through leg R2. R3. R4. And if it helps, sometimes students like to see where the ground is. It doesn't really matter where you place it, but usually we would put that at the negative terminal of the voltage source. Okay. The last thing to complete this then, let's make our analogies here. Here in electrical circuits, we're usually talking about resistance. We give this units of ohms. Right. And then the last thing to complete here is In the electrical circuit, we talk about current. Magnetic circuits, we're going to talk about flux. Okay, any questions about that kind of mapping between a magnetic circuit and an electric circuit? So let's go through an example. I hope this will help with understanding too. Okay, sorry, I got ahead of myself a little bit. Just to fill out this a little bit more, magnetomotive force F is equal to N times I. Okay, so remember this is number of turns. This is current. So just to go through a point of, I guess, a source of confusion for a lot of students in many years previous. Okay, so by drawing an electrical circuit analogy, we're mixing domains of magnetic circuits and electrical circuits, and then we complicate this by any magnetic circuit has an electrical element in it, right? So this coil here has its own resistance, it has its own current, etc. So I just, we'll go through a few examples. I hope this becomes clear, but just be sure that you're not mixing these domains. So we're going to say that current is analogous to flux, but they have completely different units. These are just analogies to help us draw electrical circuit analogies. When I'm talking about the magnetomotive force here, this is actually the current that's flowing through that coil. Okay, electrical current. Okay, so we're going to give magnetomotive force as N times I. And then our reluctance, you'll probably note that this is very, very similar to resistance that you have seen for wires in, say, your physics classes or electrical engineering classes. Is given by this equation. So this is the length of that path. This is cross-sectional area of the path. And then the mu naught and the mu r are the permittivity of free space and the permittivity of relative permittivity of the material, just like we saw before. Yes? A is in the denominator. So it looks very similar to what you've seen in what you've seen for a resistance calculation for a wire. Okay. All right, now onto the example. Okay, so what we have here is we have a reasonably complicated magnetic circuit, and then we have two loops. What would this map to in terms of actual physical hardware? I don't know, but it's a good start for us to go through some simple examples. We'll look at more complicated ones. Okay, so but basically what we have is we have a coil. We have a current going through the coil. That creates a magnetomotive force. And then we have a flux that's going to be generated by this. And this flux is going to be, we'll call phi1. And then this flux phi1 is going to split into a flux along this leg and a flux along this leg. And these each will have their own reluctance associated with them. And we want to know what is the flux phi1, which is this one right here. So we have some dimensions here, L1 and L2. You see a lot of them are the same. We have a thickness of the structure, and also we have thickness into the page of H. Right? So all these structures are three-dimensional, right? So we have some sort of finite thickness to them. Okay, so going from our analogy that we saw before, we're going to start to fill out an electrical circuit, and that's basically how we're going to start all of these problems, okay, is with an electrical circuit analogy. All right, so just mapping back to our previous example, anytime that we see a coil with a current going through it, we're going to call that a magnetomotive force, and we're going to represent that by a voltage source. Okay, so starting off, voltage source, F, and we'll just connect this bottom to ground just to make our life simple. So then my question is, what do we have next? What are our next elements to then fill out this electrical circuit analogy here? Reluctance, right? So we have a reluctance on this leg here. So I can describe this element here as a reluctance. Now, a lot of students will always ask, do I put this reluctance on the negative side of this voltage source, or the positive side? And the answer is it doesn't actually matter, right? So the flux has to go through that reluctance regardless if it's at the high potential side or low potential side of the voltage source. So I always put in the high potential side. If you like the low potential side, go for it. Doesn't matter. We're going to have a reluctance here. All right. Going around the circuit, we have reluctance in terms of we have a ferrous structure. Right here until we get to this node. All right. And then we'll see that the flux lines will split. So flux can go in this direction and flux go in this direction. So we're going to draw then reluctance here, here, so that would be here and here. All right, and then just to fill this out, we have reluctance along this leg, reluctance along this leg, and reluctance along this leg. Okay, so labeling R1, R2, R3, R4, R5, R6, and R7. So we're going to see that a lot of these are going to be the same. So this will simplify our lives a little bit, but we'll just start off with different reluctance for each of them for right now. All right, and then as a reminder, what we're trying to ultimately get to is what is the flux Phi1 that's going through reluctances R6, R7, R1. That's what we're trying to get to. Any questions about what I've done so far? Okay, so as a note, structure has some common geometries. Okay, and so the reason for this statement is if we just look at the geometry, one, the reluctance is a function of geometry and the material that the structure is made of. So assuming that the structure is made of all the same material, and then the reluctance is given by its length of that leg and the cross-sectional area of the path of that leg, you'll note that we have a typical dimension T and H for the thickness in the direction you can see here, and then the thickness into the page. And then we have some common lengths. So we see L1, L1, L2, and that's the only dimension, but we're assuming that this is L2 and this is L2 as well. Okay. All right, so we can make our life a little easier here. We can say that R3 is equal to R4 is equal to R7. which is equal to RA. And then we have R1 is equal to R2 is equal to R5 is equal to R6, which we'll say is equal to RB. All right, so that'll make our life easier. Remove variables from the equation. Okay, so if you go back to your electrical engineering class and you were to see an electrical circuit that looked like this, what would you do? What would be the first thing you would start to do? Sorry? So we would start to find equivalent reluctances or resistances for the circuit to try and simplify it so we can start to use principles like Ohm's law to then compute current, right? Yeah. So same basic process here. So the first thing we can do, you'll note that R2 and R3 and R5 are all in series. So that's really the simplest place to start here. So we're going to combine the ones that are in series. Okay, so all the principles that held for electrical circuits in terms of how you can combine resistances in series or parallel, those hold exactly here. Okay, so that makes life easier for you. So in series, they add, right? Resistances add in series for electrical circuits, so therefore for magnetic circuits, same thing. So we had 2RB plus 1RA. Okay, next we have RA is in parallel with 2RB plus RA. Right. Okay, so equation for parallel circuits is the product over the sum of those two resistances, right? All right, and then one last time, we now have everything in series. All three of these remaining reluctances are, all four of these remaining reluctances are in series. So just like the previous step, we can just, sorry, 2 steps ago, we can just add them all together, right? So we have a single, very simple circuit now, composed of a voltage source, or magnetomotive force, and a single reluctance. Okay. As a reminder, what we're ultimately trying to get to is what was phi1. Okay, so then this is just going to be Ohm's law, right? So in the voltage electrical circuit, it's V equals IR. Here it's going to be F is equal to phi times R. And our equivalent, if we want to solve for phi, is going to be the inverse of this reluctance. Inverse times the magnetomotive force, which is the number of coils or number of turns of that coil times the current running through it. R1, this is going back to the definition of reluctance. Sorry, RA, I mean, is going to be L1 over mu R T H RB is L2 mu R mu naught TH. All geometric vectors. Yes? Yeah, you're probably right. Let me check. Yep, thanks. What's your name? CR, okay. Thanks. Okay. All right. Okay. Any questions about what we did there for this problem? Okay, so slightly different problem here. We're going to now have one with air gaps in it. Okay, so we'll talk about what happens in the air gap. So as we discussed before, in a magnetic circuit, or just anytime you have a magnetic field, the field always runs from north to south, and so there must be some sort of circuit made. So it's either going to go through the air, or ideally it's going to go through the path of least resistance, which is going to be through some sort of ferrous material. Okay. So if we look at this circuit here, right, we're going to have a magnetic field here generated by this coil with current running through. It's going to create a north and a south side of this electromagnet here. All right, so then the magnetic flux is going to travel through this magnetic structure, or ferrous structure, in this direction. The ferrous structure is going to guide these magnetic flux lines, and it's going to get to a point where there is no other place to go, but it's going to then jump through the air. Right? So anytime you see this, where you have a very small gap in comparison to all the other gaps, the magnetic flux is going to go through that path of least reluctance. Okay? So we have as drawn here, this is a fairly small gap here and here. So the circuit, in terms of flux, is going to go through this, through here, and then back up. Yes. Any yes?
Do the flux lines go from north to south or south to north?
North
On
is,
the previous slide, I think you said they go from north to south.
they do go from north to south.
So here they're going downwards.
So we have, like, if we have a standard electromagnet, right, right, so we have north side on this side, and this would be then the south side. So here we have the same thing, but instead of it going through the air, it's being guided by the ferrous structure. Does that make sense?
Yeah, I was thinking like through the coil inside it.
So it is, I mean, it is going through the ferrous structure inside the coil as well. Yeah. Yes.
So on another slide, you had the magnet north and south.
Yeah.
The lines from the south to north. I don't know if that was a different case or if it was just.
Okay, did I have it wrong? Yeah. Maybe I had it wrong. Yeah. All right, thanks. All right, so first step for this one, draw an equivalent magnetic circuit. So going back to previous examples, we have something creating a magnetomotive force. So that's going to be a voltage supply in the center. All right. F. We're going to have then reluctance R1, either on the high side or the low side of the voltage source, doesn't matter. And then we're going to have the following elements. Okay, so we have reluctance associated with this leg, reluctance associated with the leg going from this junction to the end of this piece right here, reluctance associated with the air gap, reluctance associated with this length, and then reluctance associated with this bottom piece right here. Okay, so then labeling these, we'll have R3, R5, RB, and R7. All right, left-hand side is identical. Well, we have different geometries here, but so they'll have different values, but the electrical circuit analogy will be exactly the same. Okay, so some things that are equivalent here, or some things that are not equivalent starting off. RA is not equal to RB. Right, and so this is given by that we have a length. This is a little bit hidden by the line I drew, so let me redraw this. All right, so LA, we're not assuming that LA is equal to LB. Okay, so these are different lengths, so we have different air gaps on each side. So one leg is going to have a higher reluctance than the other one, okay, given this difference in length. But we do have some that are the same. So we have R2 is if we assume that this is symmetric about this axis here. We have R2 is equal to R3 is equal to R8 is equal to R9. We have R4 is equal to R6. And then we have R5 is equal to R7. Yes?
How can we assume that R5 and R4
5 and 7, yeah. So I didn't mention, Yeah, the drawing has a line of symmetry here, so that would be why. Okay, so we can, just like the other ones, we can simplify this. Okay, so we see that this entire left-hand side is in series. This entire right-hand side is in series, so we can simplify all these, combine these down. So left-hand side is going to be, if we just say R2 and R8 are equivalent, so we're going to have 2 times R2 plus 2 times R4, because R4 and R6 are the same, plus RA. All right. Similar fashion on the right-hand side. Two R2 plus 2R5 plus RB. Just a reminder, we're ultimately trying to get at what is phi A and what is phi B. Yes, in the back. The equation on the right is 2R2. Because we have R2 is equal to R3 is equal to R8 is equal to R9. All the same. Yeah, so trying to remove variables from the equation. Okay, so this is your standard current divider or parallel circuit here. So we have phi, which is going through the magnetomotive force. That's the flux for the entire circuit. That is then being divided or split at this node here, right? Okay, and that's split into phi A plus phi B. So Kirchhoff's current law holds here as well. So that means that we have phi is equal to phi A plus phi B. So you can leverage that. Kirchhoff's voltage law works for this. There are many ways that you can leverage the knowledge that you have from electrical engineering classes for these problems. So we're going to use the form of a standard current divider. Okay, so just as an aside here, well, yes, we won't get to that yet. This is a current divider. We're going to use then the form of what is the entire reluctance of the circuit. So first we're going to combine parallel reluctances on the left-hand side and the right-hand side. So just like the previous example, that's just then the product of those two reluctances over the sum. Same idea here. So I'm converting this circuit, which has 3 branches, into one that just has a single loop. So there's R1, and now I have the reluctance as the 2 parallel branches. This is going to get a little bit lengthy. All right, so this is the left-hand side, the left branch, I mean, multiplied by the right branch. Over the sum of them. All right, now if I want the entire, if I want the total flux that's going through this entire thing, so that is phi. Right, so phi is going to be equal to, using Ohm's law, is Ni over total reluctance, if I give this RT, where I can write RT as just this right here in series with R1. Okay, so I'm not going to write that out because it gets really, really lengthy. But this is basically inserting that entire term in there. Okay, so we have something. That's not what the question asked. The question asked what is phi A and phi B. So to get phi A and phi B, we're going to recognize that this is a current divider, right? So if you look back just a step above, phi running through the entire circuit, and then it splits into leg A and leg B, or phi A and phi B. Right? So current dividers, going back to your electrical engineering classes, you have some sort of current, say total current, and then this current is then split across two resistors if we're talking about electrical circuit, which has resistance RA and RB. So we have current A and current B. All right, so if I want to know what is IA, that is then RB over RA plus RB. Times the total current. All right, and if analogously I want to know what was IB, that would be RA over RA plus IB times total current. All right, so this is, take a look back at your electrical engineering notes. You probably went through this before. Or Wikipedia has this, a multitude of sources you can find this. Okay, so tying that to our problem at hand. Right, so we have a current divider. Right, we have an expression for total current, which we just, we have a flux divider. Essentially, we have an expression for total flux, which we said is just this regular phi. We know the reluctances of our different links here. And so with that knowledge, we can now turn and understand what is phi A and phi B. So I'll go through phi A. Phi B would be very similarly structured. But we can look at this and say, all right, if phi A okay, so we have two things here. When we have total flux, right, would be this whole right-hand term. So total flux is going to be Ni over, and I'll just do this as RT just to make my life easy. Right, so this would be total flux going through the whole system. My reluctance on leg A, sorry, reluctance on leg B, I mean, is 2 R2 plus 2 R5 plus RB. The combined reluctance of A and B is 4R2 plus 2R4 plus 2R5 plus RA plus RB. Okay, and then if I wanted to, I could figure out phi B just by changing the numerator right here. So phi B is similarly structured. Okay, and then the last minute or two, we'll just fill out what all your different reluctance values are. So R1, L over mu r, mu naught, and I think I have an error in my notes. No, that's correct. WT. R2. Okay, so R2 was the distance across the height of the top. I mean, the entire width, or the whole entire dimension is L. So that means half of that is L over 2, right? So R2 is going to look very similar, except it has a 2 in the denominator. R4 is going to be L minus LA over 2 mu R mu naught WT, and then R5 L minus LB 2 mu R mu naught WT. We'll get in. Sorry? So this is not the gap. This is the length of the ferrous structure here. So the 2, the half is represented by the 2 in the denominator. Okay, so just real quick, so everyone's on the same page here. If you look at the structure here, this entire length here is L, right? We subtract out, say, LB to get the remaining magnetic structure, then we divide by 2 to get what each half is. Okay. So on Friday, we'll talk about what is reluctance across the air gap. There's some things that we'll talk about in terms of assumptions we'll make on Friday. Yes? The mu's are the permeabilities of the material. Okay, so you have permeability of free space, which is mu naught, which is basically permeability of air. And then if you have a ferrous structure, that's the mu r somewhere on the order of 1,000 to 4,000. All right, well, we'll get to the air gap on Friday's class. All right, any other questions? Okay, see you on Friday.